Hey guys, this is Mr. Lowry. This is going to be your lesson for 113, which is a Wednesday if you're in Cohort A. If you're in Cohort B, then you'll watch this on the 14th, which will be a Thursday. So our lesson today is on similar triangles here, and we're actually going to cover a couple sections of the textbook. We're going to hit a few of them. So this is actually 6.1, 6.2, and 6.3. We're going to focus on 6.3, but we kind of have to go back and hit some ideas from 6.1 and 6.2 first. Okay, so we're gonna pick up some ideas. Actually, these are going to be some review ideas from probably 8th grade, and we'll build our way up to what we're talking about here today. Okay, the first key concept for today that we need to talk about is proportions. Okay, what is a proportion? How do we solve a proportion? What does proportional mean? That's kind of where we're at. So I'm going to give you a scenario, and we're going to just kind of draw this out a little bit so you don't have to write quite as much. But let's imagine that you have a postcard, okay, from way back in the day when people mailed stuff. Okay, so a postcard, let's say its dimensions are about 5 by 3 inches. Okay, and let's just say you can kind of pick your own scenario what kind of postcard it is. But for me, I'm going to pretend that this is a postcard of Korean super pop group BTS because they're so hot right now. So let's say you wanted to take this postcard and you wanted to enlarge it so you can make a poster and you could put it on your door. Okay, so we're going to make this kind of thing bigger. When we make it bigger, though, we don't want it to be distorted. We don't want the image to be messed up. Okay, so we're going to have a poster here, and we'll make it kind of bigger. Obviously, our drawing won't necessarily be to scale, but let's say we have our poster here. And let's say we measure the door. This is going to go on our bedroom door. And in order for it to fit the way we want it to, we want it to be 22 inches wide. Okay, and we don't care necessarily about the height, but remember we just want it to be proportional, which in this case means that the relationship between the height and the width stays the same. We don't mess it up. We don't distort it. The image doesn't look stretched or skewed in one direction. Okay, so we don't know how high to make our poster, but what we can do is we can set up what's called a proportion and solve a proportion. Okay, so a proportion is an equation. Okay, it's just a specific type of equation where you have a ratio equal to a ratio. So I'm going to write a ratio here. A ratio is a comparison of two quantities. Okay, so here's ratio 1. And this is a comparison of the original width and the final width that I want, right? So 3 to 22. Now you could write this as a fraction, and you can kind of simplify this fraction or whatever, find a decimal approx, and see what that relationship is. But the idea here is if we don't want the image to distort, this relationship has to be the same between the original height and the final height. Okay, so this is what's called a proportion, right? It's when two ratios are set equal to each other. And what we're trying to do is we're trying to preserve a relationship here between original and final. Okay, now this is not the only way to set up this proportion. You could have done it a couple different ways. This is just one way to do it. But to solve a proportion, what we're going to do is we're going to cross multiply. Okay, so what I'm going to do is I'm going to multiply across kind of diagonally here, 3x, 3 times x is 3x. Okay, and then I'm going to multiply this way, 22 times 5. That's going to give me 110. And that gives me an equivalent equation, right? So this is, if this is true, then this is true as well. Okay, so that's like the cross multiply strategy. Okay, so let's write that down. That's how we solve proportions. Okay, now we need to finish this up, so we're going to divide both sides by 3. And this isn't going to come out super nice, so I'm going to use my calculator here to get my exact fraction. Okay, so that's 36 2/3. We're talking about inches, right? Okay, so that's kind of just a review on proportions and solving proportions. If you look in your textbook, this is on page 282. you got a bunch of stuff about proportions, which you should probably already know, again, from 8th grade. But you got some key concepts here, like the word ratio is a comparison of two quantities, or kind of a relationship between two quantities. We have this proportion, right? Proportion is an equation stating that two ratios are equal. And then it talks about this cross product idea. Some of these terms you don't necessarily need to know, like extremes, means, cross products. Not super important for our purposes. But again, it's kind of a quick review. And then there's this key concept down here, property of proportions, which we're going to talk about in a second. So it says for any numbers a and c and any non-zero numbers b and d, because you can't divide by b and d, these are equal to each other if and only if AD equals BC. That's basically showing you cross multiply. Now this maybe is a little small for you to see, but you can pull out your textbook on page 283 and take a look at what that looks like. Okay, what I want to show you though is this new property is actually just a property we already know. Okay, so if you think about what's happening here, let's look back at our proportion that we solved. All we really did is we used the multiplication property of equality twice. Okay, so let's kind of go through that real quick. Let's say I wanted to get rid of these fractions. Okay, well, I could multiply both sides by 22, right? Multiplication property of equality says that's okay. These are going to cancel, and then I get 3 equals. And if I turn this into a fraction, 5 times 22 again is 110. X times 1 is x. So I get this guy. Okay, now I just use that multiplication property of equality again to get rid of this denominator, right? And I have 3x equals 110. So it's not really magic. It's not a new property. It's just the multiplication property of equality used twice in a row to get rid of both denominators. It's basically clearing the fraction, which we've talked about before. Okay, so the other thing that I want to put down here in this section is what proportional means, the word proportional, because we're going to use that word in a second. Okay, proportional basically just means that the relationships between quantities are preserved. So this isn't a formal definition, but some ideas. We want the relationship to be preserved. Okay, in other words, we have equal ratios. Okay, so in this case, what are the relationships we're preserving? Well, the relationship between the original and the final has to be the same as the relationship from the original to the final for widths and heights. So this relationship of original width to final width has to match the relationship between the original height and the final height. That's what we're trying to preserve. Otherwise, we're going to have a skewed picture. Okay, so proportional. There's some relationship between quantities that's preserved, which is going to give you equal ratios. So those are some kind of important ideas. All right. Okay. The next idea that we're going to talk about, I'm going to turn to the textbook first, and then we'll add it here in your notes. But this is actually going to be from 6.2, section 6.2. So, actually, sorry, made a mistake. Before we do that, let's go back to the notes, and let's practice solving a couple of proportions. That was my goal. Sorry about that. So let me give you 2 example problems that you can take a look at here. We'll make these a little bit harder. Okay, so example A, and then example B. Okay, so copy those guys down. And once you have them down, you can go ahead and pause the video here. We'll give everybody a couple minutes to solve those, and then we'll come back to the video and see if we got it right. Okay, if you're coming back from pausing, you should have these 2 guys done. Let's go ahead and do them really quick together. One thing to keep in mind is that in some of these ratios we have binomials, right? 2 terms. And if that's the case, we need to make sure we distribute. So we're going to use our cross-multiply strategy here, or cross-product as they call it in the in the book. We just need to make sure we distribute, and also keep in mind that this is really just the multiplication property of equality twice. So let's do this guy. So 2 times 3x minus 5. I'm going to write it like this so I don't forget to distribute. Okay, so these two multiplied. Okay, and then I have 4 times negative 13 on the other side of the equal sign. Okay, so 6x minus 10 equals, that's negative 52. Okay, add 10 to both sides. We just got a two-step equation now. 6x equals negative 42. Divide both sides by 6, and you got x equals negative 7. Okay. Over here on the other side, we have a binomial over a binomial, and that's okay. No big deal. Just make sure you distribute. So we got 2 times x plus 5 equals, don't forget your equal sign. Sometimes when people cross multiply, they put everything in one expression, and that's obviously going to mess you up. Okay, so we need an equation. If we start with an equation, we should, continue to have an equation as we go. So we'll do a little distribution here, and then we'll group all the x's on the right. That'll give us 3x over here. Group all the numbers on the left. That'll give us a 15 over on the other side, and we're going to get x equals 5. Okay. Okay, sorry. So that's kind of your rundown of 6.1. Okay, now let's go to 6.2. So grab your textbook and open up to section 6.2, which is on 289. Okay. Okay. This is this is on similar polygons. So we're basically just stopping here in this section, just to get the idea of what similar means in terms of geometry, because it's a specific definition, and learn how to write and interpret a similarity statement. So you got a definition here that we'll kind of write down. So here's an important idea. Polygons that have the same shape but are different in size, they're called similar polygons. Okay, a polygon is just a generic term for a shape with a bunch of sides. So like triangles have 3 sides, quadrilaterals have 4 sides, pentagons have 5 sides, and so on and so on. So we're just talking about shapes with a bunch of sides, and if two polygons are similar, then they have congruent angles, but the sides aren't congruent. Okay, it turns out that the sides are actually proportional. This is probably a little hard for you guys to see in the video, but you have your textbook in front of you, so this is what we want to write down in your notes. So this idea here is important. 2 polygons are similar if and only if their corresponding angles are congruent. So we get congruent angles. And the measure of their corresponding sides are proportional. That's a word we just talked about, right? Proportional means the relationship is preserved, or we have equal ratios. Okay? So in this shape, all of these guys have, in these two shapes, A is congruent to E, right? B is congruent to F. D is congruent to H. We're talking about the angles. C is congruent to G. But also notice that the relationship in the sides are the same, right? So like 10 over 5, that's 2. 5 over 2.5, that's 2. 6 over 3, that's 2. 8 over 4, that's 2. In other words, all the sides here are like half as big as these ones, or all these are 2 times as big as over here. So we said they're proportional, right? It's almost like we either scaled this one down or scaled this one up, just like the poster idea that we're talking about. We want to preserve the relationship between the sides. Okay. All right, and then we got the similarity statement, which is super important. So last week we talked about congruent statements, and we spent a little bit of time on there, because I knew we were going to talk about similarity. So here's your similarity symbol. It's like the top of the congruence. It's called a tilde. It's a little kind of swooshy shape. It looks like a congruent symbol, except it doesn't have the equals under it. Okay, so you say similar to. So if we have this quadrilateral ABCD similar to EFGH, the position of those letters tells you what parts correspond to each other. So A and E, right, they're both in the same position. So angle A corresponds to angle E, right? B and F are in the same position, so angle B corresponds to angle F, and so on with the angles, right? Notice I have 4 congruent angles. Okay, now the sides are not congruent, so that's really important. They don't have congruent sides. If 2 triangles are congruent, they have corresponding congruent sides, but these are not congruent. They're proportional. Right? Similar shapes have proportional sides. So what you see is equal ratios, right? The ratio of AB to its corresponding side, EF, is 2, right? 5 over 2.5. That's also equal to the ratio of BC to its corresponding side, FG, right? 6 over 3. So all of these 5 over 2.5, 6 over 3, we're going to have 8 over 4, and then 10 over 5. It's all equal to 2. We have these equal ratios. And that's a super important idea. Okay, so 289, really important page for us. Let's kind of add some of that to our notes here. Okay, so this is our second key concept. Okay, and what we're going to do is we're going to practice with similarity statements. Okay, so we're going to call this interpret a similarity statement. All right, now just like we did last week, I'm going to do this without even a picture of the shape because I think it will help. Sometimes the shapes can make things confusing, or the figures, if they're not pointed the same direction. So let's write something down here. We're going to use a triangle, okay, and we're going to write ABC similar to XYZ, okay? And just like that part of the book that we just looked at, that green part, we're going to write some proportions, and we're going to write some congruent statements. Okay, so 2 triangles that are similar. That means they're different sizes, but they look like they're the same shape. Okay, so what we know from here is if we have this similarity statement, we'll kind of label that similarity statement. Okay, ABC congruent to, or sorry, not congruent to, similar to. Okay, then let's line up the angles. Okay, we know that angle A is congruent to angle X. Not similar. We don't say that an angle is similar to another angle. That's not the case. We say that they're congruent to each other because we know in similar polygons, the angles are actually congruent. Okay, we know angle B is congruent to angle Y, and we know that angle C is congruent to angle Z. Again, because of the position in the statement, right? These both are in position 1, these both are in position 2, these both are in position 3. Okay, now let's talk about the sides. Okay, we don't say that they're congruent, we don't say that they are similar, we put them in proportion. We actually write a proportion. And so we're going to actually write a 3-sided proportion. So let's start with AB. Okay, AB is one of our sides, and that matches to side XY. Position 1 and position 2. But we don't say that they're equal, we don't say they're congruent, so they're similar. We actually put them in a ratio. Okay? And we say that that's equal to the next pair of sides. So let's go BC, right? The one that connects vertex 2 to vertex 3. Okay, BC corresponds to YZ, so we put them in a ratio. Okay? And then we got A to C, and the corresponding side to AC is YZ because it goes from vertex 1 to vertex 3, or XZ. Okay, and so this is what our relationship between the sides are. Okay, we don't say that sides are similar to each other. We don't say AB is similar to XY. That doesn't mean anything to us. Okay, we also know that AB is not congruent to XY. Okay, so don't get confused and try to write that out. That's not the case. What we have is proportional sides, meaning we have equal ratios. we match each side to its corresponding side, and we make a ratio of them, and we know that that ratio will be the same across the rest of the triangles there. Okay. Okay, let's do a couple example problems here using the idea of proportionality and solving proportions. Okay, so let's do a couple example problems with triangle similarity. So we're going to solve for x with similar triangles. Okay, so we're going to draw this picture out here, and we got a couple triangles. It's going to look a little bit like this. So kind of an hourglass shape here. Okay, we're going to call this C, D, S, R, and we're going to put some measurements here. Okay, the last thing we need here is a similarity statement. So let's say we know QRS is similar to QCD. All right, now the picture itself is helpful, but really we want to pay attention to this guy. Okay, the similarity statement allows us to match up the corresponding pieces. Oh, we need one more vertex, Q. So we have these numbers here. We know that if these two triangles are similar, then their sides are proportional. And so what we really need to do is we need to set up a proportion. We just got to figure out how to read this guy. Okay, so let's just start out by just doing what we did up here with the sides. So QR. Okay, what does QR correspond to? QC. So we put those in ratio. Okay, what about RS? What does RS correspond to? RS corresponds to CD, so we put those guys in ratio. Okay, and then we have QS is the other side, first to third, and that has to correspond to QD. Okay, and so each side of the first guy is over its corresponding side. We put them in ratio. Okay, make sure that you go in the right order, right? Don't put like one of these over one of these. It doesn't really matter which order you do it in at first, but once you pick that order, you gotta kind of stick with it. So let's see what pieces we have. We don't have all the pieces, but we do have this guy. Okay, so CQ or QC, that's this guy. Okay, and QR, that's this guy. Okay, so QR over QC is this over this. Okay, supposedly that should be equal, if these are similar shapes, that should be equal to RS over CD. Okay, so let's see if we have that guy. We don't have those, so let's go to the next one. So QS over QD. QS is 33 over QD, which is 22. All right. Okay, so now we solve this proportion. Now there's more than one way to solve it. We have been talking about cross multiply. If you wanted to, you could actually simplify this here, since these both have a common factor, and that would be fine too. I think I'm going to do it that way. If you didn't do that, you would still get the right answer, but let's go ahead and simplify to make our lives easier. Okay, now let's cross multiply. So that means 2x plus 2 when I distribute is equal to 30. So 2x is equal to 28, or x is equal to 14. Okay, so on your homework assignment for tonight, you're going to have, I think it's 6 problems like that, where you are looking for a missing value. In this case, we're looking for x, right? But the way you do that is you use the similarity statement to set up and then solve proportions. Okay, similar polygons have proportional sides to each other. So use the similarity statement to understand what sides, the relationships with the sides, and then you can replace those numbers with what you have. Okay. Now in this one, of course, we didn't have these two sides, but it doesn't matter. We really only need 2 sets here. Okay. That's the end of this video. We got one more idea to talk about, and that's just how do we, show that triangles are similar, and that will be in the next video. So make sure you tune into that one as well.